So everybody can start making their way back to their seats. All right, we're going to get started, folks. It's right around 20 after, a little maybe a minute or two after that. By just a simple showing of hands, how many of us started out in CB radio? Started out in CB radio. Happy 10-4 day.
Good evening. Good to see all these smiley faces here. I'd like to introduce Kevin Jackson, AA3V XV, and he's our guest speaker tonight. He was licensed since 1978, first licensed in the UK, and he's held the call sign G4 NEJ since 1978. After moving to the USA for a new job opportunity in 1997, he was licensed as AA3 XV. He is very active on HF and always has a new antenna he's either working on, designing, or using. He's been designing satellite RF communication systems for commercial, DoD, and human spaceflight applications, throughout his career. Currently, he is the Chief Technical Officer for Flexitech Aerospace based in Orlando, Florida, designing radio communication solutions to meet today's challenging satellite communication needs. He holds patents for deployable spacecraft antenna designs and has contributed to over 40 satellite programs for the ISS, including working on a console in mission control. Before he founded Flexitex, he was a senior scientist and chief engineer for the Cygnus spacecraft's resupply missions in the ISS and orbital ATK. He holds a MSEE and BSEE degree in satellite communication engineering and electronic engineering from University of Surrey in the United Kingdom. Thank you, Kevin, for offering to do this program for us tonight. I'm looking forward to learning a lot.
You forgot to mention one thing. Ed, you forgot to mention one thing. He's live, not on Zoom.
I'm real. Instead on Zoom. Who's got the charts? So I'll answer the question that everybody asks me when they meet me. Where are you from? So I originally grew up in Portsmouth in England and was interested in electronics. I joined a ham radio club at 15 years old. I didn't know that was going to be my career. I spent the rest of my career designing RF communication systems, and I've got to work on some just amazing stuff and still do. I consider myself very lucky. And I often tell people everything I ever wanted to do with radio, I've done and more. And the interesting thing is I go to work all day and I do RF communication systems and antennas, and I come home and do more of it. You can never get enough. Okay, so we're going to talk about antenna testing and antenna measurements, because we've all got antennas and we tend to just, you go and buy an antenna, you plug it in and you hope it works. But there's a little bit more to it than that. And I just wanted to talk about how do you measure antennas? How do you design antennas? I've put together a lot of antenna designs, a lot of them flown in space, some very big antenna arrays in space. And it's always very thrilling to see something you designed actually work and deliver the communication performance that you expected. Okay, let's go to the next chart. Okay, so what is an antenna? We've all got them, but there's definitions of what an antenna is. But they disappeared. Okay. You good? Okay. So what are antennas? I've just tried to sort of set a landscape for antennas. They enable electrical signals to be radiated, electromagnetic signals to be radiated. We all know that. We talk to each other or we talk across the world. If you're on 10 meters these days, you can talk anywhere. Last weekend was just amazing on 10 meters. And that's your electromagnetic energy radiating from the antenna and reaching out over long distances. It's also called non-ionizing radiation. So if you go into a lab where they're doing this type of work, it'll say on the door, non-ionizing radiation on the door, just to make sure you know what you're putting yourself up for. And you do not want to stand in heavy or strong RF fields. That's something you do not want to do, which is why the FCC now have you do that analysis that nobody wants to do, but you have to do to find out how much RF energy there is around your antenna system and whether you're giving that to the neighbors as well as your own children and your family. And so it is important you understand that. So there are 4 basic classes of antennas I put up here. The element antenna, we've got loads of element antennas where we've got dipoles for HF, and we've got whip antennas and those sort of antennas. Traveling wave antennas, and here's an example here in this picture. A traveling wave antenna is a helical antenna. And there are other types of traveling wave antennas as well. And there's arrays. And this array in this picture here is called a log periodic dipole array. And there's apertures. And apertures could be, here it's a parabola, but it could be a horn antenna. These are all aperture type antennas. So these are just broad classes of antennas. And the direction of radiation is depending on the design of the antenna. So your antenna could be omnidirectional, like the antenna you put on your car, which radiates all around the car, or it could be like a Yagi antenna or a beam antenna. If you're lucky enough to have that big tower with your 3 element on 10 meters or whatever it is, then you got a lot more gain in a single direction. And the RF energy is also polarized. So depending on the type of antenna and how you energize that antenna, you can have horizontal and polarization or vertical polarization or circular polarization. And there are classes of circular polarization as well, depending on what the application is. So when you're doing a circular polarization, you can generate a circular polarization with a helical antenna, like in the picture here, or you can get 2 Yagi antennas and put them at 90 degrees to each other on the same boom, and then feed them out of phase, 90 degrees out of phase, and you get circular polarization. And depending which phase you feed them in, you can get left-hand or right-hand circular polarization. So all of these things you can generate from manipulating basic designs. And so the field of polarization, the reference that you're measuring, that is known in when you're doing antenna measurements, called the E field. So you're measuring the E field. There are 2 radiation from an antenna, and one of them is the E field. And in the next chart, we'll just look at that a little bit more. Let's go to the next chart. Right. So polarization. And I said there's linear polarization, horizontal or vertical, and you can see that in this diagram up here. Let's get my electronic pointing stick here. Point in the right direction and not blind myself. So there's horizontal and vertical. There's horizontal radiation and vertical radiation here. Circular polarization, left and right hand, and you can see this is rotating one direction, this rotating the other direction for left and right hand circular polarization. And then, so the basic rule, if you stand behind a helical antenna and you look down a helical antenna and it's in this direction going away from you, then that's right hand circular polarized. And often I stand behind helicals and say to people, that's right hand, and they say, how do you know? So it's just, you can just see by looking from behind it. So most ham radio antennas, though, are linearly polarized. So you have a Yagi or a vertical. Those antennas are polarized in a linear fashion. It's interesting, the beacons around the world. I've just done a lot of work on HF beacons. And all the beacons around the world are vertically polarized. And then I realized this after I was trying to listen to them on a horizontally polarized antenna, and they're not very strong to me. What if you use a vertically polarized antenna? They're much stronger. So VHF and UHF antennas for ham radio can be linear or circular polarized, and it depends what you're going to do. If you're doing satellite work, then you would want circular polarization. If you're going to do long distance or weak signal stuff that George does, then you would want to be probably horizontally polarized, ideally, but you could be vertically polarized. Go to the next chart for me. So what's gain? What is antenna gain? We talk about antennas having gain, but they don't really have gain in the sense that an amplifier, like I talk in this microphone and you can hear it, there's gain between this microphone and those speakers. An antenna doesn't have real gain. It has directivity. And the directivity comes from the way that it focuses the RF energy coming out of the aperture of the antenna. So the gain is really a measure of that focus. How much energy can I take and focus it? And I'll show you on another chart how you would measure that. But the amount of focus that you give to the RF energy that you put into the antenna and the direction it goes in is a definition of how much gain that antenna has. If you put 10 watts into an antenna and it's omnidirectional, it get radiated all around the antenna. But if you put 10 watts in and there's a focusing mechanism like a Yagi antenna, then that 10 watts gets radiated in one particular direction. So it gives the appearance of having gain, but it doesn't really have gain. So can we measure the gain of the antenna? And here's a radiation pattern here of an antenna. Can we measure the gain of the antenna? You can, and you can do it quite simply. And when I show people how to measure gain of antennas and measure and actually derive a pattern of an antenna as well, they're actually shocked at how easy it is. I went to a big commercial facility recently. They built a parabolic, a dish antenna to go on a spacecraft. And I went there and said, well, we're taking the parking lot. I'll measure it for you. And I'll tell you roughly how much gain it's got. And they were really shocked that I took all this stuff out in the parking lot and measured exactly what the gain and the directivity of that antenna looked like. And when we took it to an anechoic chamber and remeasured it, it wasn't much different to what I measured in the parking lot. And so you can measure antennas fairly easily, and I want to show you how to do that, because if you're interested in making those measurements, you can do them yourself. We'll roll into the next one. So there's all these terms you see: dBi, dBc, dBd. You see them in all the spec sheets, and you read them and you go, "Oh, that sounds really nice." Yeah, but actually, those have real meaning, and they're related back to how a source of an antenna is measured and how the gain of that antenna is measured. So you need a reference to measure gain against. You can't just say, my antenna's got 4 dB of gain. You have to measure it against some reference. And the reference they use, and this is where the I comes in dBi, is it's measured comparing it to an isotropic radiating source. So what's an isotropic radiating source? It's a point, imagine a point source, a bit like that laser I have here. It's a point which is radiating energy evenly in all directions. And on the surface plane of that is your zero reference on that outside of that plane. So now if I take that energy, as in this picture here, and I take that energy and I focus that energy in one direction. And I take basically all the energy that's in that isotropic radiated sphere, and then I start focusing in one direction. Then the radiation in that one direction is greater than the zero we measured when it was radiating in all directions, and that's the apparent gain. And that's where we get dBi from. dBi means dBs above isotropic. So that's where it comes from. And a dipole as a standard, and this is always a good standard to have because if you want to measure things, is that a dipole is 2.15 dBi gain. And this is really useful if you're going to measure antennas, because even if you don't know the antenna you're doing the measurement with, if you make yourself a dipole for a certain frequency, then you can measure the difference between that dipole and the antenna that you're using and get a difference between the two. And here's, I brought a couple of dipoles with me, and this is a 300 megahertz dipole I used for it. It was used to measure a spacecraft antenna in a chamber. But this is a very simple dipole. And we know what the gain of this is 2.15 dB. And we can make it horizontal or we can make it vertical. And actually, I have one here which we drive with a servo. We have a servo motor inside the chamber. We can just flip it over from one to the other. And this one has a tiny, tiny ballon on it as well, a matching ballon, which is hand wound. And somebody, I think, had asked me, how the hell did you make that? Yeah, you need a much bigger one. This won't be a lot of good, I don't think. So that's how we measure gain. So what is DBD? DBD is reference to a dipole. Nobody wants to tell you the gain of your antenna, your ham radio antenna in DBD, because the number's lower than dBi. So they like to tell you what it is in dBi. So they tell you, oh, it's 10 dBi gain antenna. But if I did that in DBD, I'd have to take 2.15 off of it. So they don't want to tell you that number. But it's in commercial systems, and when you're doing measurements for particular applications, often there's references to DBD as being the term that they want to use. And people will send specs and say, you know, I want an antenna that does this in DBD. And then the other one they come up with is DBIC. What do they mean by that? dB isotropic circularly polarized. So you'll see this written in specs if you're doing commercial antenna work. They write DBIC, and when I first saw that when I was much younger, what the hell's that? But I'm not going to ask anybody because I don't know. So I was flicking through books trying to find out what it is. But that's where these come from, these terms. Flip on the next one for me. So what do we need to measure when we measure antennas? I'm sure everybody in this room has done some antenna measurement of some kind, right? Even if it's a VSWR meter. So you want to measure the VSWR, voltage to standing wave ratio, and you can do that with a simple bridge. You can dual meter or the nice cross meter ones. I have one of those. That looks pretty cool, the cross meter ones. Or you can measure the same thing as VSWR, but you can measure what they call S11. S11 is radiating energy into the antenna and measuring how much that energy is reflected back out. It's port 1 to port 1. That's where the S11 comes from. And you can measure that with a vector network analyzer. And you can buy it, and I have one here with me. You can buy those vector network analyzers on Amazon.com for about $70. And I'll show you, you know, what you can do with a vector network analyzer you cannot do with a VSWR meter. It tells you a lot more about what's going on inside your antenna and how that's matched to your cable. And then, as I said, you can measure antenna gain. And so the simple way to do that is you need two reference antennas to be able to measure antenna gain. You put the two antennas about 7 to 10 wavelengths apart, so you can tell that you have to be very careful about the distance you've got to do the testing in, because you need to put those antennas. Why do you need to put them 7 to 10 wavelengths apart? Because when you're inside that distance, you're in what's called the near field. When energy radiates from an antenna, it organizes itself as it radiates away. And the final organization into the beam that you would see in the distance, the received signal, is not organized until it gets 7 to 10 wavelengths away from the front of the antenna. So you have to do those measurements at least 7 to 10 wavelengths away. Now, as antennas get larger, and you want to do this in an anechoic chamber, and I've often done these sort of measurements, you need a bigger and bigger and bigger chamber to do these measurements in to get 7 to 10 wavelengths apart. So what do you do then? Well, you go outdoors and you do the measurements on an outdoor range. And I've got a couple of pictures of outdoor ranges coming up. So you can put the antennas, reference antennas, 7 to 10 wavelengths apart, and you take a measurement of the signal strength that you get with two reference antennas. Then you substitute your antenna for one of the antennas, and the difference in signal strength is the gain of that antenna. And you could measure that with a very simple vector network analyzer, like this little nano VNA you can buy on Amazon.com. Or you could measure it, and one of the good ones I found is SDR Play software-defined radio. It has a very accurate power meter on it. So you can actually measure that and use that as a way of recording what the gain difference is between one antenna and the other. And of course, the signal strength difference in dB, that is the gain. The other thing you can do once you're doing this sort of measurement, you can measure antenna patterns. You can actually take a pattern, what we would call a pattern cut from the antenna, so you get an idea of what the actual radiation pattern of the antenna looks like, a bit like we had in a previous chart, but I'll show you some more of those. So as I said at the bottom here, accuracy of all these types of measurements depend on where you measure them, how high the antenna is off the ground, how far the antennas are apart. Do you have any reflections from things? If you go into an anechoic chamber, it has absorptive material on the walls, so any RF that radiates out is absorbed in the walls. So you only see RF from the source. If you do it outdoors, it bounces off buildings, and if you did it in here, you wouldn't get a very good measurement. You could probably do it in the parking lot and get no bad measurement out of it. And I'll show you a very simple diagram of how we do that. We roll on the next chart. So there's the three options for measuring VSWR, and I obviously didn't spell that correctly. VSWR, return loss, S11. What can you measure with? We got the little nano VNA here. So I love this little device. You can buy this on Amazon between $40 and $70. It's a really nice little screen it has on it. And you can buy some, it comes with software. The software's free. Ham radio, everybody likes free. So the software for this is free. So you buy this and you plug it into your computer and you get a very basic vector network analyzer, a very complex way of measuring antenna performance. And the amazing thing about this, I took this into my RF engineering lab and I measured an antenna with this device, and I measured it with a $40,000 vector network analyzer. And the disappointing thing is the results were the same. Telling you that I wasted $40,000 on the network analyzer. So I've told loads of people, go and buy yourself one of these. This is an amazing tool for measuring antennas. It is actually better than an antenna analyzer. An antenna analyzer gives you some data. This gives you everything. It gives you the impedance. It gives you the S11 or the measurement. And you can actually change this from measuring S11 to measuring VSWR, and it puts VSWR for you on the screen. And this is $40 to $70. You can get one that's $1,000. There's some really nice ones that are $1,000. There's some really nice ones that are $10,000 too, but that's not the range of possibility. But this is a really nice tool to have, and they are very, very cheap to go and buy. And of course, the classic bridge. We all started with one of those. I have one I've had since 1978. I just can't get rid of it. It's just a nice, classic old thing. And that's, of course, what you did in those days was you tuned up and down the band. You saw what the VSWR was one end of the band, tuned down here. Then you went up to your HF antenna, you snipped a bit off. Or if you're smart, you didn't snip it off, you folded it back. Then you went back and you measured it again, and you tuned up and down the band again. Then you went and folded back a little bit more till you got it tuned to the frequency you want. And I think, Ed, we were talking about that earlier. You keep tweaking and tweaking until you get it to the right frequency. But it's laborious doing that way. With this little guy, you can do that really quickly, because it'll tell you where it's really tuned. So you know if it needs to be shorter or longer. You're not guessing and you're not tuning up and down the band. It's very easy to do. Okay. So I have a buddy hex. If you know the buddy hex antenna, if you want a buddy hex, you have to wait 7 months for one. So I ordered it at Dayton Hamvention. 7 months later, Chris called me from the company and said, hey, I've got it for you. So I got my buddy hex. I was very excited. And I've got the mass works for it to go on with a little cranky handle. If you've seen that, it's very nice. And my wife was going out of town for 3 days. So, oh God, this is the weekend. All we're going to do this weekend is we're going to get that buddy hex and we're going to put it up and we're going to have a load of fun. And I did. I put this up on the patio there, you can see, and assembled it and put it 6 feet off the ground. And then I went into the lab on Friday before I left, and I took a $10,000 VNA home with the computer it goes with. And I took it out and I measured it. So we go to the next chart. So I put it at 6 feet, and then if you roll to the next chart, not rolling. There you go. So there it is, buddy hex, 6 feet above the ground. By the way, you could do this with the little VNA, but why would you do that when you can go to the lab and borrow the $10,000 VNA? So this is actually a copper mountain VNA. Very nice handheld. The VNA the size of a pack of cards. It measures to 6 gigahertz from 1 megahertz. It's an amazing tool. But it's a mini VNA of this type, and I use a little Surface laptop to run it on. And so here's the results. If you look, so the antenna's at 6 feet above the ground. Here's where it's tuned for all the different bands. This is starting at the bottom here. This is 20 meters. And then we got 15 meters, 17 meters, etc. going up the band. Here's 10 meters. And you can see they're all not tuned in the right place. So the little markers here, frequency markers, you can see the dip is actually here, but actually it's tuned there. I wanted it at 28.5 megahertz, so I can hunt all that DX. Well, that band was packed this weekend. If you were on there, that was interesting. New Zealand, Australia, it was all there. So it's tuned higher than expected. So if we go to the next chart, we push that antenna up now to 20 feet. Look what happens. It retunes, and now it is tuned to the right place. This is actually the 6 meter section of that buddy hex. That's an amazing antenna, by the way. That buddy hex, you put it together, it works. And I now got it on a rotator, and it's a really great antenna. And actually, I called Chris and said I did put 1.5 kilowatts into it, and it did survive, because he said nobody's ever done that. I actually changed the connector to an SO239 because it has BNC on it, and it works. It's really nice. So you can see the height of the antenna above the ground matters. You can't just put an antenna up, and Ed and I were talking about, putting wire around the fence and doing stuff like that. It'll work, but it probably won't be tuned to where you want it to be tuned. Whereas when you raise it up on the mast, you push the mast up. If you've seen those there, that's a really nice mast as well. You put it up, you put the guys out, and this is the result you get. It improves the overall tuning. Let's go to the next chart. So the other thing you can look at with this little guy, this guy is and you can see maybe in the background here, let me just turn that on. You can just see there's a little Smith chart in the background, just like this. This is a Smith chart. What's a Smith chart? If you ask an engineer, they're here wax lyrical for 2 hours telling you how wonderful a Smith chart is. I'll tell you one thing you need to know about Smith chart. In the middle is 50 ohms. That's all you need to know. The rest of it is superfluous information, unless you want to design something and spend hours on the bench messing around. The middle of that chart is 50 ohms. So what you want to see when you put your buddy hex up and you put this antenna on there is you want everything, all those little numbers for all those different bands, the 14.2, 18.1, etc. By the way, you want those all nicely clustered in the middle, because that means that it's all tuned around the 50 ohm point. And you won't need to get the tuner and push the button. And actually, with my buddy hex, you can just take the tuner completely out, and it is matched well enough not to require the tuner. Fortunately, I have the Elecraft K4D with the amplifier, and the amplifier, as he says to me, no, I don't need the tuner. It actually tells you that amplifier. So the buddy hex is really good. And you can see this is where a VSWR 1-to-1 would occur right in the middle of that chart there. So you can see it's pretty good. You see the impedances are listed here for you. And this gives you some additional information about whether it's upwards above the 50 ohm point or below the 50 ohm point, because it's inductive and capacitive above and below, which is why all those tuners have those nice rolly inductors and capacitors in them. But you don't need to know that. You just need to know it's 50 ohms in the middle. That's the important thing. Okay, let's roll on the next one. So how do we measure gain of an antenna? You get 2 masts, and I have 2 MFJ masts, the ones with the tripods you can fold out. And I have a patio. Now, let me just tell you, people ask me, how do I get away with doing all this on my patio and my wife doesn't complain? Because her father was just like it and she thinks it's normal behavior. I married well. He's a great guy. I'm so grateful. He flew model planes, he played with radios, he did it all. So she thinks it's quite normal. So what you do is you get 2 MFJ masts, and you put ones, if you put one at the door there and you put one over here and you put your 2 antennas, then you get your 2 dipoles and you put your 2 dipoles on there. There's one here. These are 2 identical dipoles. I had one of my engineers make these up to test a log periodic dipole array we flew in space. And we put one of these at either end of the range. And so where our office is, the guys next door call us the scientists, because we're always out in the parking lot with 2 big masts with antennas on them and writing things down and looking very studious. And so we have this set up, and I actually take this home, put it on the patio when I want to do my own measurements. So you have two known antennas. You put them 7 to 10 wavelengths apart, and you need a signal generator and a receiver. Now, the greatest way to do that is with a VNA, one of these little VNAs. And if you put this on 0 span, so it's not sweeping any frequency, it's on one frequency, you can generate a frequency on one side from one of these ports here, and you can receive it on the other port and just put a long coaxial cable between the two. If you're worried about how much loss there is in the cable, if you measure it on the VNA before you start, you know how much loss there is in the cable before you even start the measurement. And then you measure these, take a measurement on here on what it says in terms of signal received. Then the next thing to do is to put your reference, to change your antenna. So you change it for something else, change it for the thing you want to measure. You put this in at one end, take one of the dipoles out, put this in at one end. And now you measure the difference. And the difference is the gain. And we studiously write that down in a little book, just like this. So we use these. These are really nice antennas. They're from WA5VJB. He's become a legend. By the way, if you ever go and see a stage show, you go downtown to the theater or something, and you see those black triangular antennas that's actually one of Kent Britton's antennas. That Shaw Microphones buy them and put them in black covers so you can't see they came from him. And it's this antenna that's inside there. Kent's a nice guy. If you ever want to talk to Kent, he's antenna mad. He's like me. This is a 400 megahertz to 1000 megahertz log periodic array, which you can do for use for simple measurements. Great if you're doing ham radio. I've used these for 70 centimeter measurements to measure antennas I built for 70 cents. So this is how you do this. There are many different ways beyond the VNA to measure this. You can buy a USB signal generator. The company here in Florida makes those, and they make a signal generator in a little stick like a thumb drive. That goes from around about 20 megahertz to 4 gigahertz, that little generator. It's a couple of $100, but it's going to cover every antenna you ever thought of. And then at the other end, you can use an SDR play. I have 3 of those different receivers. They're great receivers for measuring. Or you go and buy, as I said, a nano VNA like this. And that's how you measure gain. It's very easy. You just take a signal strength meter reading, then you replace it and take another reading, you've got gain. Okay, let's go to the next one. So there you go. Here in this picture, and this is what I did recently. I did a parabola in a parking lot in Denver. I told them I'm going to come up and do the measurement before it got cold. That was part of my stipulation of coming up there and doing the parking lot test. But we measured a parabola using exactly this type of methodology. Okay, let's go to the next one. So how do you plot patterns? So to plot a pattern of an antenna, what you're looking for is varying gain. And all you have to do is do the same measurement as we just did, take the reference measurement, and then at one end with your antenna you want to measure, rotate that antenna around and take measurements at, say, 5-degree steps. Now, I've managed to automate all this with a vector network analyzer, so I've got it completely automated. You just actually push a button and it does it all for you. It rotates around. But it's fairly cheap equipment. I've got a TV rotator that you'd have on the roof of your house, which came from Channel Master. And a Channel Master rotator, I can tell you, rotates in exactly 59.5 seconds. So in 59.5 seconds, it does 360 degrees. All you got to do is either move it 5 degrees and make a measurement, another 5 degrees, make a measurement, and write it down, and then put it into Excel, and it'll draw you a nice little plot of the antenna. Or you can automate it and measure it with a VNA and store it as a file. And that's how we do it. We store as a file, rotate it around, you get an antenna plot. So we go to the next guy. So there's what it looks like. That's a raw antenna plot using that method. You get the individual numbers off of this and put them into an Excel spreadsheet, and you can actually make it so that you can see a 360-degree version of this. This is a polar plot rather than just having this type of flat plot here. But this gives you the full 360 degrees, and you see this antenna's got a nice peak in the middle of it. That's how it should look. This is actually a Yagi antenna that we measured. It's actually on a spacecraft, which flew very, very recently, 400 megahertz. The great thing is about a lot of the antennas we build, they're right at 70 centimeters. So what we have done is taken them outside and doing a space station pass. I've got a 705 in the office and 818 I keep in the cupboard, and we take them out and we've got a few moments to go and work a few people over the ISS transponder, which Lou knows well. And I tell you, if you do that, if you take some of the young engineers I have and you take them outside and you talk to a couple of people over the space station, it blows their mind. They say to me, I can't imagine you just did that. You talked to some guy in Canada or through the space station. And they can't imagine. So this is a really good way to connect engineers to the fact that ham radio is a pathway to them having a lot of fun. So this is what you get. You get a nice plot out of Excel. And you can then manipulate it in any way you like. Let's go on to the next chart. So here's an antenna test range. These are both NASA measurements. I've been up to many different ranges, NRL, NASA's range. I've been to the Johnson Space Center, Farfield range. I've done a lot of antenna measurements there. They had the Orion capsule in there last time I was in there doing some measurements. But this is the Mars rover here. They're doing antenna measurements on the Mars rover. And this is a large deployable antenna they're doing on the outdoor range. And you see there's some, at the bottom here, this spiky stuff here. This actually is anechoic material. What they're trying to do is stop reflections off of the ground. This is your biggest problem when you do outside measurements, is you want to be really high up because RF is going to bounce off the ground and it arrives and distorts the pattern of the antenna. So the way to cool that down is to absorb that RF by laying this, what we call RAM material or absorbent material in front of the antenna. That's what they're doing here. Okay. So simulations, there's lots of ways. So you see magazine articles and they show you pictures of a simulated antenna. And I always look at those and go, yeah, sure. Let's see, I'd like to really measure what that antenna looks like. So you can do simulations in EasyNet. You've probably seen that. You can buy that software quite easily. You can do mathematical models. You can do Excel. I've done Excel spreadsheet models as well of antennas, so you get an idea. But you can do simulations. But take that pattern with a grain of salt, as I say here. That pattern is only as good as the performance of the real antenna. So we're going to the next one. Didn't flip. Oh, it did. Sorry, I didn't see it. Okay, reality. So in reality, antenna patterns, as I said, ground reflections, reflections off buildings, the matching of the antenna, surrounding structures, said here, the materials you use to build the antenna, they all make a difference. You can use one material against another material and it has a dielectric content, it'll change the antennas. You could model that with very complex software. There's a software package called HFSS, which everybody say, oh, have you got HFSS? They only want to ask you that because it's $50,000 to buy that software. But they model it in HFSS. The other way you can do it is in MATLAB. So in my lab, we have MATLAB Antenna Toolbox. That's a nice modeler to use, but it only gets you so far. So I've trained all the engineers now. They know that it only gets them close to the result. Now go build one. And I challenged them. I said, you model the antenna, I'll build 3. I'll tell you which one works best. In the same time it took them to model it. So those things are not viable for ham radio. Let's go on to the next one. So here's a helical antenna. The design objective is 13 dB IC. So that's dB isotropic circular. Right-hand circular polarization, 1.4 to 1 or better VSWR. I ran an Excel model. I just did it by hand. I just know all the parameters for a helix. I put them into Excel, calculated what it should be. This is 1296. Spacing of the turns, etc. And there's an optimization with the turns. This is when sort of tribal knowledge helps, because I can tell you 0.2 to 0.5 is the right number. If you don't know that, then it's difficult to figure that out. But there's the calculations. We're going to the next one. So there's the MATLAB simulation. So we put it into MATLAB Antenna Toolkit, and this is what you get. It turns out this very nice pattern for you. And these are great to go into for meetings. You go to a meeting or design review, you take one of these, they go, oh, that's really nice. They think everything's going to be fine. It says the gain's 13.7 dB. I input all those things. Actually, I didn't. I have to be honest, I had an engineer do this for me, put the stuff in and generate this. So we go on to the next one. So there is that 23 centimeter antenna. It's a helix. It's uses FR4 printed circuit board material in the center. It's actually a steel wire with copper plating on it. It's a ground plane that's 0.75 of a wavelength. That's the magic number, by the way. 0.75 of a wavelength is what you need by a helix. And it has a tubular balun you can see sticking out the back, because a helix is naturally 150 ohms impedance, and you've got to transform it to 50 ohms. So the tubular balun I designed there, transform it to 50 ohms. We go to the next. So here's a simple measurement. This is taken in a parking lot, exactly as I told you. Just measured in the parking lot. Just a simple S meter or spectrum analyzer, or however you do it, but this is the result you get. Told me the gain was 14.5 dB. I'm going to the next one. And so here it is at anechoic chamber. Now you get the real result. Gain is 13.7 dB. Actual ratio is outstanding, 0.98. And cross polarization is 11.5. So that shows you the difference. Simulation to actual measurement, and interesting, a parking lot measurement to an anechoic chamber. Let's go on to the next. So lessons learned. Simulations get you close, but they don't get you there. You can simulate an antenna in EasyNet, but if you don't pull it high enough on a tree or whatever, after you built your HF antenna, it won't work like you expected. Expect to tweak it, adjust it, tune it. You've got to do that. It's not just going to work. And I learned from bitter experience, keep notes so you don't go, how the hell did I do that? And because you'll remember, it's write it all down. Find a measuring device you like and learn to use it. Buy a mini VNA, best investment. Use for gain and pattern measurements, impedance measurements, whatever you want to do. Okay, next shot. Okay, so books, reference books, I'd recommend Rothammel's. This is an outstanding book. This is the best antenna book for practical ham radio use you will ever see. Maybe the ARRL don't like me telling you that. There's a theory book in the middle, Konstantin Molinas. He's an amazing author, but he's all about the math and all that stuff, and that's not so interesting maybe unless you're doing a master's degree. And then there's the ARRL antenna book, all great books. The 3 top books, they're on my shelf, use them regularly. Okay, next. So finally, the magic solution. I just wanted to show you this. I was wandering around Akihabara, and if you know where Akihabara is in Tokyo, I did a lot of work on the space station in Tokyo, on the space station systems. And in Akihabara, I found this can of RF. I thought that's pretty cool. And the other one my brother sent me last week, it's a new ham antenna spray, pumpkin spice. Great. Great for the lowest VSWR. Okay. Okay. Okay, any questions? Sorry, those. Yeah. And no, it's actually, that is the reason that reflection is there, because it's off the ground. The RF energy is reflecting off the ground and back up into the antenna. I actually discussed this with George because we're trying to figure out, what's going on there. Anything else?
Phased 20-meter vertical antenna.
Yeah.
If you added additional elements that were unconnected, would that make
passive? Yes. So it would affect the pattern. If you put passive tune to the same frequency passively and the right distance apart, it would give you directivity. Yeah. Yeah. It would certainly distort the pattern. George? Yes. Can't measure them. So they do modeling. And they do, I've talked to those guys. I did go to one of those stations, 250 kilowatt radiating station. The guy with me wouldn't go in the tuning room, but I did. You could hear the AM on the tuning cage. Actually, about this. So Lou's got a model of antenna that we did together that actually we flew in space. It's a helical, a very, very long helical that we flew in space. Is it? Yes. All antennas, because they are balanced. So an antenna is a balanced element. So if you get a dipole like this is actually balanced. The coax feeding it is unbalanced. You have to transition. If you don't, you can not use a balun, but a lot of the RF ends up coming back down the coax. So you end up with radiation off the coax. In general, you need to match it's about 72 ohms, 73 ohms. Yeah. Yes, always. Yes. Yes. You, even if it's a one-to-one match, because you're going from coaxial unbalanced to a balanced antenna, you should use a balun. Yes, Roth Hamels. That is the book. It's about $45 to buy. That is the best book. I bought one for every engineer in my office as a gift. So they do read it because I make them read it. I go, what does it say in Roth Hamels? They go, oh, I don't know. I'll go and look. But it's a great book. And there's a lot of stuff about there about baluns in there. There are books like Baluns and Ununs. That seems a little bit dry when you read that book. But Roth Hamels is just a bunch of ham radio people collected all their wisdom in a book. It's about this thick. Anything else? Yeah. Yeah. Right. But there, yeah, but yeah. Yeah. There you go. Yeah. It's a coax. So if you wrap some coax into a, and I was telling some of this in a lab the other day. Yeah. Mm-hmm. I've used those on VHF antennas for spacecraft. Yeah, it's a balun. About the antenna performance, what you need to measure it in some way. Yeah, that's hard work. Yeah, I would go and buy a mini VNA or something, or an antenna analyzer or something. That's the way to do that. Yeah, I mean, that's all you really need to know. That's really, you want to know where the antenna's tuned, and it's very useful to know what the impedance of that antenna is. That's the other part of it. Okay. No, no. Everything, everything. Yeah, everything affects your antenna. Yeah. Sorry. I would use cross Yagis because you can switch them left and right hand. Lou has those. I have them too. I have a 77 one and a 2-meter one. Feed them separately, and you can switch LNAs between them as well. And then you really want a tracking head. Don't try the hydraulic pointing thing. You distract you from working people on the radio. That's what I would do. Yes, yes. It could be a dish. It could be a helical. It could be a Yagi. A Yagi with two Yagis on one 90 degrees apart. Yes, all satellites are, well, yeah, in a box. Yeah. Yes. 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 You can do that. But satellite, you see, if you're doing a ham radio satellite, the satellite is slowly tumbling over. See, once circular polarization, because that little, monopole antenna on that satellite is moving around like this all the time as it's going over you. And it happens at the space station too. So the best thing is run circular polarization. So GEO spacecraft run, some are linear for special reasons. Most are circular polarized. And they run left-hand, right-hand circular polarization at the same time. It's a linear polarizer, it's loose antenna. I have another payload on space station that uses another one of a loose antenna, but it's a linear polarized. It's actually a monopole hanging underneath. Some great pictures in the NASA database of it. You really want to use the circularly polarized antenna to access that. That's what I do. I use a egg beater, one egg beater and one antenna I designed myself, circularly polarized, and I get coverage from horizon to horizon. I work a ton of people on there every Friday. I don't work in the office on Fridays and spend all my time on ham radio. That's my gift as I got older. Okay, took enough time. I'm good.
Huge, thank you. Kevin, would it be okay to send your PDF out to the group?
Yes.
Okay. Yeah, okay, we'll do that. All right. Real quick, before we do the drawing, just want to remind everybody, next month's meeting, November 1st, here in this room, 7:30. And our guest speaker will be Michael Walker, Victor Alpha 3 Mike Whiskey, Flex Radio. So. Yes, because I did forget about that. Come on up here, real quick.
Thank you. Hey, everyone, Joe, KQ4 AID. We had our hams in the park last month. Great turnout, biggest one yet. The next one's going to be October 21st, again at Central Winds Park, because that seemed to be very conducive for us. And people were operating off to the side on their own. They were analyzing and troubleshooting antennas, learning how to use gear. So there was everything from soup to nuts going on. So if you can make it out, October 21st at Central Winds Park.
Excellent, appreciate it. All right, going into the drawings. Again, your choice. If you win, first ticket pulled, last three digits, 067. I'll go ahead and pull the next one. All right, next one. Somebody said higher, so 117. Okay, your choice. And finally, last ticket. Okay, right in the middle. 100. Come on up. Got the antenna. Don't forget, if that is not the right antenna for you and you need one, you HRO up on Winter Springs, they'll swap it out for you. Great credit toward the other one. There you go. Appreciate it, guys. Again, next month's meeting here in this room, November the 1st. See you there.
Be safe.